So my lecture today is meant to be background for what I'll explain Tuesday. Well, I'll be talking about new work on interpreting in terms of gauge theory, a new twist on geometric Langlands developed in that paper. And it was based in part on earlier work by Teschner. I know he's a lecturer at the school, so perhaps you'll be hearing from Teschner about his work in this direction. So, but today's lecture will be mostly a review about earlier work on gauge theory and geometric Langlands. So in the gauge theory approach, the starting point for geometric Langlands is n equals 4 super Yang-Mills in 4 dimensions, where the gauge group is either G, a compact Lie group, or it's Langlands GNO dual group, G dual. And the theory based on G has a gauge coupling and topological angle theta, which combine to a complex parameter with positive imaginary part. There's an elementary symmetry that shifts tau by 1, which just has to do with the fact that incident number is an integer. And likewise, the dual theory has an analogous dual parameter, also with an elementary symmetry. But the claim of electromagnetic duality is that the theories based on G and G dual are actually equivalent with this equivalence. And that's not particularly a statement about geometric Langlands, and people studying it usually ask questions with no obvious relation to geometric Langlands, but we can specialize to the situation that leads to geometric Langlands. So for this, we consider a particular topological twist that leads to a CP1 family of topological field theories, parameterized by complex parameters psi or psi dual. Twisting simply means that you pick a linear combination Q of the supersymmetry generators, such that Q squared is 0, and then you pass it everywhere to the cohomology of Q. You only consider operator states and boundary conditions that are Q invariant, modulo Q exact operators and states. So CP1 comes in because there are a pair of supercharges that any linear combination of which squares to 0, which you want to use here. Q can be any non-zero linear combination. And then psi just parameterizes the choice you made of the linear combination. So if you study the whole family, you get an equivalence. Well, first of all, a highly quantum equivalence here, and a more trivial classical equivalence. And together, this becomes the duality of what's called quantum geometric Langlands in the math literature. But for today, we're going to set psi equals 0 or infinity, and we'll study the basic duality between psi equals 0 for the A model of G and psi dual equals infinity for the B model of G dual. I call them the A model and the B model because they are closely analogous to what are called A models and B models in two-dimensional mirror symmetry. So in general, quantum field theory in dimension D associates a number to a D manifold, a vector space of physical states in D-1 dimensions, and a category of boundary conditions in D-2 dimensions. For geometric Langlands, we'll just consider 4 manifolds that are product sigma times C. C is an oriented 2 manifold that we keep fixed, and we only vary sigma, another 2 manifold. So we define a category of boundary conditions that depends on C. It's convenient then to draw 2-dimensional pictures where we only exhibit sigma. So for example, if sigma has a boundary, then to formulate quantum field theory on sigma, we need a boundary condition, like I've drawn here. There would be a boundary condition describing what happens on this left boundary of sigma. Boundary conditions make a category in math language, given 2 boundary conditions, B1 and B2. The quantum field theory assigns a vector space to this picture, which mathematically would often be called the space of the Hom space from B1 to B2. And with this definition, Hom from B to B is an algebra for every B. So we simply consider this kind of 2 manifold with 3 boundaries labeled by B. Coming in at the bottom are 2 copies of Hom from B to B. Going out at the top is 1. And a similar picture with 3 instead of 2 guys going in and 1 going out would show that the composition from Hom B to itself that comes from this picture is associative, although not necessarily commutative. Similarly, by considering a more general case like this one, you learn that, for example, Hom from B1 to B2, well, you learn that you can compose Hom from B1 to B2 with Hom from B2 to B3. And if I'd chosen B2 to B3, we would have learned that Hom from B1 to B2 would be a module for the algebra Hom from B2 to itself, and so on. So it's important also that there are two ways to visualize Hom from B1 to B2. It could be an open string joining onto the rest of the picture, but it could be simply a local operator insertion at which a boundary condition is jumping from B2 to B1. You can think of the equivalence of these pictures as coming from a conformal mapping that projects an infinite strip to just a point on the boundary. So for these pictures to be equivalent, we don't need topological invariance. Two-dimensional conformal invariance would be enough. So in conformal field theory, you'd think of the open string here as going off to infinity as an infinite strip, and you'd say you made a conformal mapping from this picture on the left to this one on the right. So what I've been explaining is basically that two-dimensional topological field theories correspond to categories. So electromagnetic duality will give an isomorphism between the category curly C associated to C in the G theory at psi equals 0, and the category C dual associated to C in the G dual theory at psi dual equals infinity. In addition, there's a natural mapping between certain natural functors on C and C dual. These functors come from line operators of quantum field theory. So in a quantum field theory on a manifold M, a line operator is some sort of modification of the definition of the theory along an embedded one manifold K. The natural line operators at psi equals infinity. I didn't understand the request I just got to start the video. I have no idea how to.
Your video is not on. I don't know if that's on purpose or we can't see you. We see the slides, but we cannot see you.
Ah, it's not the. Ah, sorry. Okay, sorry.
Okay.
I didn't start it again after you had me unshare and you had me leave the.
Yeah.
Restart. Okay.
But now we share. Yeah.
So I was saying that we wanted to find certain functors on one category and dual functors on the other category. These will come from line operators of quantum field theory. In general, in quantum field theory on a manifold M, a line operator is some sort of modification of the definition of the theory along an embedded one manifold K. The natural line operators at psi equals infinity are called Wilson operators, the holonomy of a connection, interpreted as an operator in quantum field theory. The natural line operators at psi equals 0 are 't Hooft operators. In physics, Wilson and 't Hooft operators are usually used for problems like analyzing confinement of quarks and other subtleties involving universality classes of quantum field theories. But in comparing to the usual language in mathematical discussions of geometric Langlands, a line operator is a functor from the category of boundary conditions to itself. We can understand that from this picture. So at A, I've simply drawn a boundary B with a line operator parallel to the boundary. But in topological field theory, the distance between T and the boundary doesn't mean anything. We could think of T as being moved way up to the boundary, and we just get a composite boundary condition made up of B and T. We can call it TB. That explains how T acts on objects of the category. Its action on morphisms is shown in B. In B, as I explained a moment ago, morphisms can be represented by points on the boundary at which the boundary condition jumps from B to B prime and perhaps then to B double prime. And you can see that by moving T up to the boundary, we get jumps from TB to TB prime and then to TB double prime. And from such pictures, you can see that the axioms of a morphism are satisfied. A functor are satisfied. So I've been drawing pictures in 2 dimensions, but 2 more dimensions are not drawn, and T really depends on the choice of a point in C. Such pictures make it obvious that the line operators TFP and TFP prime commute. In a purely 2-dimensional picture, it would be well defined whether P is to the left of P prime or to the right, and therefore it would appear that TFP times TFP prime, acting on B with TFP and then with TFP prime, might be different from acting in the opposite order. But when you take into account that there are two more dimensions, it's clear that you can move TFP through a TFP prime with no singularity, and therefore the TFP and TFP prime must commute. So, and the same could have been said for W on the other side. So the two dual categories are equipped with dual families of functors, parameterized by the choice of points in C and some other data, and commuting at distinct points. So TFP are the usual Hecke functors of geometric Langlands, which, as I'll tell you Monday, originated from a construction of Narasimhan and Ramanan, while W of P corresponds to its dual and usual geometric Langlands duality. Since these functors depend on more data, a representation of the dual group, you can also consider the composition of Hecke functors at the same point P, but associated to possibly different representations. And basically the same argument by taking the limit, distinct points, and then taking the limit as the points coincide, shows that they commute. The duality will also say that the algebra of composition of Hecke functors at the same point is the corresponding algebra of Wilson operators at the same point, which on elementary grounds is the tensor algebra of representations of the dual group. So the product of holonomies in two representations R and R prime is the holonomy in the tensor product representation. And then you can expand the tensor product representation in a sum of irreducibles. And that will match the corresponding decomposition for 't Hooft operators. So as I've said, Wilson operators are just constructed from the holonomy of a connection, but 't Hooft operators are more subtle. So let me briefly describe how 't Hooft operators are defined and how they're related to the geometric Hecke transformations in geometric Langlands. So the A model, analogously to the 2D A models that are related to the Fukaya category and mirror symmetry, localizes on the solutions of some elliptic PDEs. If we consider a time-independent situation with 't Hooft operators that run in the time direction, then we can reduce to three-dimensional PDEs. In general, we'd have four-dimensional PDEs. But to save a little time, I'll consider only a time-independent situation where we can localize on time-independent solutions, and then we get three-dimensional PDEs, which are simpler to describe. These are the Bogomolny equations. The Bogomolny equations are equations for a pair A and phi. A is a connection on a G bundle E over a three manifold. W3 for now is just an oriented three-dimensional Riemannian manifold. Phi is a section of ADE, the adjoint bundle derived from E, over W3. So in other words, phi is an adjoint valued zero form. And in terms of the curvature F of the connection A, the Bogomolny equations say that F is star dA of phi. dA is the gauge covariant extension of the exterior derivative, and star is the Hodge star, which here maps one forms to two forms, since we're in three dimensions. So this is an equation among two forms. So the Bogomolny equations have a lot of remarkable properties. For example, Etienne Hitchen wrote a book about them. And we're just going to focus on one aspect. So we consider the Bogomolny equations on a product of R times a Riemann surface C. Now, any connection A on a G bundle over C determines a holomorphic structure on E, or more exactly on its complexification. You just write the D sub A as a 0, 1 plus a 1, 0 part, and you use the 0, 1 part to define the complex structure. In complex dimension 1, there's no integrability condition for a D-bar operator, so this gives an integrable complex structure on the complexification of E. So the fact that every A defines a holomorphic structure on the bundle is an important fact that, for example, will also come up Monday in relation to the Narasimhan-Seshadri theorem, or the way Etienne Bott interpreted it. So in this case, for any Y in R, by restricting E over R times C to E over Y times C, we get a holomorphic bundle E sub Y over C. But if the Bogomolny equations are satisfied, E sub Y is canonically independent of Y. Indeed, a consequence of the Bogomolny equations is that d bar A is independent of y, this R should be y, up to conjugation. If we parameterize R by y, then, well, then part of the Bogomolny equations are this. In other words, the Bogomolny equations are equations for one form in 3 dimensions. But part of that is a one form in 2 dimensions. And the 0, 1 part of the equation, sorry, well, I should have said a 2 form, but anyway, a component of the Bogomolny equations gives this. And this equation tells you that d bar A is independent of y up to conjugation. It tells you what conjugation you have to make of d bar A to make it independent of y. So as long as the Bogomolny equations are satisfied, E sub y is canonically independent of y as a holomorphic bundle. The Bogomolny equations admit solutions with the singularities at isolated points in R3, or in a more general 3-manifold W3. However, I'll state it first for R3. First, for U1, you fix an integer n, and you observe that the Bogomolny equation has an exact solution for any x mod in R3. The solution is that, first of all, this is phi. Well, first of all, for U1, phi is valued in the Lie algebra, but the Lie algebra is trivial for U1. So phi is just a 0 form, and this is the 0 form we pick. Then f is a 2 form, which is star of d phi. That formula defines f and not a connection A whose curvature is f, or the line bundle L in which A is a connection. But such an L and A exist and are essentially unique up to gauge transformation if n is in Z, if and only if n is in Z. So that's the basic solution. Now, more generally, for an R3, since the Bogomolny equations are linear, they have a unique solution with singularities labeled by specified integers, n1, n2, and so on, at specified points in R3. So here I've labeled a bunch of points by integers. In the context of the Langlands correspondence, the integers ni should be understood to label representations Ri of the dual group. For G equals U1, the dual group is just U1 again, and an irreducible representation is labeled by an integer, which physically is called the charge. So these singularities, this physicists would call this the magnetic charge of the isolated singularity. And this magnetic charge is dual to an electric charge for U1, for the dual group, which also is U1. Now all this was completely invariant under rotations of R3. Now pick a decomposition of R3 as R times R2, and think of R2 as a Riemann surface C. Suppose the singularities are at points yi times pi, where yi is in R and pi is in C. Well, as long as y is not one of the special values with one of these singularities, the indicated solution of the Bogomolny equations determines a holomorphic line bundle Ly over C, and this naturally extends to Ly over CP1 if we compactify C2 to CP1 by adding a point at infinity. That's the case because the singular solution I've described decays rapidly enough at infinity that there's a canonical compactification over CP1. Ly is constant up to canonical isomorphism for y not equal to 1 of the yi. But even when one crosses 1 of the yi, Ly is constant if you restrict it to the complement in TP1 of the point pi. You see, at a given yi, there's a singularity, but only at one point pi in C. So even when you cross a singularity, the line bundle Ly is constant if you remove 1 point from CP1. In crossing y equals yi, Ly undergoes what's called a Hecke modification, which in the abelian case just means it's tensored by the line bundle O of pi to the ni. O of pi is the line bundle trivial away from pi, whose sections are allowed to have a simple pole at the point pi. Now, the solution describes a sequence of Hecke modifications of a line bundle over C. The modification is made whenever at any value of y where you cross one of these bad points yi, and then you get a Hecke modification at the point pi in C. We can do something similar for any simple Lie group G. Let T be the maximal torus of G and little t its Lie algebra. Pick a homomorphism from the Lie algebra of U1 to T. Up to a Val transformation, such a homomorphism is equivalent to a dominant weight of the dual group, so it corresponds to a representation of the dual group. We turn the singular solution of the U1 Bogomolny equations that we already used into a singular solution for G simply by composing it with rho. So rho of A and rho of phi are a singular solution for G. Then we will look for solutions of the Bogomolny equations for G with singularities of this type at specified points. So the picture is the same as before, except now the points are labeled not by integers, but by representations of the dual group. Also, now the equations are nonlinear, so there's no simple way to superpose solutions. But still, I've described a singularity that a solution should have at each of these points. And so we can look for solutions that have the right singularities at all those points. So the same type of reasoning, well, first of all, for each sort of vertical slice at a fixed y, where y runs in the horizontal direction, a solution describes a holomorphic G bundle over CP1. And the holomorphic type of the bundle describes when one jumps across one of these bad points. And the jump is precisely a geometric Hecke modification, as first described by Narasimhan and Ramanan, and later used in geometric Langlands by Balanson and Drinfeld, and then many others. Kronheimer in the 80s was the first to analyze this situation and showed that the space of solutions of the Bogomolny equations on R3 with these singularities and trivial at infinity is a hyperkähler manifold. If you impose the boundary condition that the solution decays fast enough at infinity, what you actually get is a space of Hecke modifications from the trivial bundle to itself. Now let's look again at the picture that told us to interpret a line operator T as a functor in the category of boundary conditions. Well, you see that if in this situation we have a gauge theory over the 3 manifold, or well, the 4 manifold, the 2 manifold I've drawn and the hidden 2 manifold that isn't being drawn, the Riemann surface C, you see that whatever bundle you have near the boundary jumps when you cross T and is replaced by something else. So T will act on the bundle that's defined by the boundary condition on the boundary by a Hecke modification. So then a more careful analysis shows that the Hooft operators, the action of the Hooft operator on boundary conditions precisely matches the action of the Hecke functors described by Balanson and Drinfeld. To go into a little more detail, I want to introduce a useful language for a simplified version of geometric Langlands duality. So let M sub H of G and C, or just M sub H of G, be the moduli space of G Higgs bundles on C. As shown by Hitchin, it's a hyperkähler manifold. In one complex structure, it parametrizes Higgs bundles. In another complex structure, it parametrizes flat bundles over C with the complex structure group G sub C. G sub C is the complexification of G. So I and J are Hitchin's notation. Hitchin referred to as I, the complex structure where his moduli space parameterizes Higgs bundles, and J was the one where it parameterizes flat bundles with the complex structure group. Then IJ and K equals IJ act as the unit quaternions and are part of a hyperkähler structure. So geometric Langlands duality can be understood for many purposes as mirror symmetry between the A model of the Higgs bundle moduli space in symplectic structure omega K and the B model for the dual group in complex structure J. This instance of mirror symmetry was first studied mathematically by Hazel and Thaddeus in 2002, and they showed that this is a rare case where the Strominger-Yau-Zaslow picture of mirror symmetry can be made completely explicit. So Hitchin had the Hitchin fibration for these moduli spaces, and the Hitchin fibration in this context turns into the Strominger-Yau-Zaslow special Lagrangian fibration associated to mirror symmetry. Now you can definitely ask questions where the two-dimensional picture is inadequate. Mathematicians describe this by saying that the theory should be formulated on the stack of G bundles, Bun-G, not on a finite dimensional moduli space. Physicists describe it by saying that the correct formulation is as a duality of four-dimensional theories. 4 is the minimum. There's a 6-dimensional formulation that explains some things better, but that's not for today. The two descriptions are not so different because and Bott showed in 1981 that a model of Bun-G is the space of all connections on a fixed smooth G bundle over C. So a four-dimensional gauge theory is a two-dimensional theory with target Bun-G. So this story of and Bott will also come in on Monday when we're talking about the work of Narasimhan and Seshadri. So the four-dimensional gauge theory, to describe it more in the language mathematicians use usually when working on geometric Langlands, is a two-dimensional theory with target Bun-G. But for many purposes, you can make a low-energy approximation and describe it as a two-dimensional theory whose target is the Higgs bundle moduli space. I want to use the two-dimensional description as mirror symmetry to explain why the category that appears on the G or automorphic side of the duality is a category of D modules on Bun-G. The most familiar branes in the A model or Foucault category are Lagrangian branes supported on a Lagrangian submanifold L. But Kapustin and Orlov discovered that in general, you can also define Coisotropic A-branes that are supported on a coisotropic submanifold above the middle dimension. The construction of coisotropic A-branes is delicate in general, but the simplest case is the case relevant to geometric Langlands. They had a simple condition for coisotropic A-brane of rank 1, whose support is all of Y. Suppose we're studying the A model of Y with a symplectic form omega. Suppose also that the model has a B field, which I'll just call B. For our purposes, the B field is a closed two-form that appears as a contribution to the action of a two-dimensional sigma model. Consider a rank 1 A-brane B endowed with a Chan-Paton line bundle L over Y that has a unitary connection of curvature F. The Kapustin-Orlov condition for this data to define a coisotropic A-brane in the A model of symplectic form omega is that omega inverse times F plus B should be an integrable complex structure on Y. So we view, I is naturally a linear transformation of the tangent bundle Ty of Y, and the Kapustin-Orlov condition should be that I squared should be -1 and should define an integrable complex structure. If you're only given Y as a real symplectic manifold, in general, you'd have trouble satisfying this condition. But in the case relevant to geometric Langlands, where Y is the Higgs bundle moduli space, Y is actually a complex symplectic manifold that we're viewing as a real symplectic manifold with the real symplectic form being omega k, the imaginary part of a holomorphic symplectic form. Precisely in that situation, there's an easy solution of the Kapustin-Orlov conditions, which Kapustin and Orlov actually described in the original paper. So we simply solve the Kapustin-Orlov conditions by taking F plus B to be omega j. And then since omega is omega k, the imaginary part of a complex symplectic form, and F plus B is omega j, the real part, we get that omega inverse times F plus B is omega k inverse times omega j, and that's I, an integrable complex structure, because Y was given as a complex symplectic manifold. So I'll call the A-brane constructed this way the canonical coisotropic A-brane BCC. On Tuesday, it'll be important that we also could have taken F plus B to be minus omega j, and then omega inverse times F plus B is minus I, another integrable complex structure. The various ways to satisfy F plus B equals omega j differ from each other by B field gauge transformations. For today, I'll just take F to be 0 and B to be omega j. It turns out that additively, A, which is Hom from BCC to itself, is the algebra of holomorphic functions on Y in complex structure I. but the algebra structure is different. A is a deformation quantization of the commutative ring A0 of holomorphic functions on Y in the sense we described yesterday. I'd like to explain a little of how that comes about. So remember that ordinary deformation quantization of the ring of smooth functions on a real symplectic manifold is given by a path integral in a circle where we integrate over maps X from a circle to M, and the action is given by this simple formula, the holonomy around the circle of the pullback of a connection on a pre-quantum line bundle. A pre-quantum line bundle is just a line bundle whose curvature is the desired symplectic form. I think I should have written a 1 over h bar here to be coherent with this formula. I omitted it because later we set h bar to 1. In the context of deformation quantization, one usually studies this path integral perturbatively in h bar. In perturbation theory, you can assume the map X from S1 to M is almost constant, so it extends in a natural way up to homotopy to a map X from D to M, where D is a disk with boundary M. So we could have written the action as minus I over h bar times the integral over a disk of x star of omega. And incidentally, that shows that deformation quantization, as opposed to quantization, depends only on omega and not on the choice of a pre-quantum line bundle. Now, in the path integral, we make cyclically ordered insertions. And so then we compute the path integral that I wrote before. But now I just rewrite it, where I'm thinking of the action as being given not by an integral over the circle, but by an integral over a disk whose boundary is the circle. The map X has been extended over the disk, and in the action I have x star of omega. That way of writing the action is unnecessary for deformation quantization, what will be useful in a moment for the A model. Now, to make contact with what we're interested in for geometric Langlands or for brane quantization, we assume M can be complexified to a nice complex symplectic manifold Y with symplectic structure I and complex symplectic form omega. Where nice means that the sigma model of Y actually exists as a UV complete quantum field theory. For instance, that's true if Y is a complete hyperkähler manifold. And moreover, we want Y to have a holomorphic symplectic form omega, whose restriction to M is the A model symplectic form little omega of the A model of M that we're interested in. Sorry, I said that wrong. The restriction to M is supposed to be the symplectic form we want to quantize for quantizing M. So then the space of maps from S1 to M, which we integrate over in deformation quantization, can be complexified to the space curly W of maps of S1 to Y. Let's also assume that the functions we're trying to consider in deformation quantization are restrictions to M of holomorphic functions on Y. In deformation quantization or in ordinary quantization, we'd have no reason to make a restriction like that. But in brane quantization, we do. And I'll be describing brane quantization in a moment. Then deformation quantization of M can be cast in the following form. What we're trying to integrate is the restriction, see, W naught, okay. W is a complex manifold, an infinite dimensional complex manifold of maps of S1 to the complex manifold Y. If Y has a real involution with fixed points at M, then W has a real involution with fixed points at W naught. But let's forget that real structure for the moment and just analytically continue everything in deformation quantization. So the path integral measure of deformation quantization analytically continues to a top dimensional volume form on the complexification, the space of maps X from S1 to Y, the complex manifold. Everything here and here complexifies, where the F is complexified because I assume there are restrictions to M of holomorphic functions on Y, and this complexifies because omega is the real part of a holomorphic 2 form on Y. So the deformation quantization of M can be reinterpreted as follows. The integrand of deformation quantization, which is this, can be viewed formally as a holomorphic form of top degree on the infinite dimensional complex manifold curly W. A holomorphic form of top degree can be integrated on a middle dimensional real cycle. In the present case, that would be a path integral over some middle dimensional real cycle in the space of maps of the circle to Y of this integrand. Well, what could be a middle dimensional real cycle? There's a standard choice, which was the original integration cycle W naught of maps to M rather than to Y. But any other gamma will give something that satisfies the general conditions of deformation quantization. In other words, with any gamma, such that the path integral converges and makes sense, we're going to get, with insertions on the boundary, a deformation quantization of the ring of commutative functions that will satisfy general properties of deformation quantization. That'll be true because in a formal power series expansion in powers of H bar, we don't really see what the integration cycle was. Any integration cycle could be used from the standpoint of a formal expansion in powers of H bar. My statement that we could use any integration cycle on which the integral converges generalizes the following fact. Let X be an algebraic variety of finite dimension, lambda a holomorphic form of top degree, and gamma a middle dimensional cycle. If X is not compact, we should further stipulate that gamma is a cycle in which the integral I'm about to write converges. Then, first of all, we can consider this integral for any gamma restricted so the integral converges if X is not compact. And these periods will often satisfy differential equations that can be proved by integration by parts. And when that's the case, these equations do not depend on the choice of gamma. So the statement that the differential equations don't depend on the choice of gamma has an analog in infinite dimensions, that we get deformation quantization of the ring of functions regardless of gamma. But what's a useful middle dimensional integration cycle other than the obvious one of maps to the real subspace? Well, one answer, which is actually important in representation theory, is that Y might have different real subspaces. And then you learn that deformation quantization of different real subspaces is related to the same Y, which is actually important in representation theory. But for our purposes, there's a different answer, which is actually simple. With D being a disk whose boundary is S1, we can take gamma to consist of maps from S1 to Y that extend to holomorphic maps of D to Y, where these maps are pseudo-holomorphic in an almost complex structure K, in which M omega is of type 1, 1 and positive. If Y is actually hyperkähler, which it is for geometric Langlands, then K is part of the hyperkähler, can be chosen to be part of the hyperkähler structure of Y. So, well, we're back in this picture, but, oh gosh. Okay, sorry. I had a version of the picture where the interior of the disk was shaded to indicate that now it became real. But I see, unfortunately, in the slide, I've used here the wrong version of the picture where it's still unshaded. But imagine in your mind's eye that this disk has become real and is now an essential part of the story. Before, it was just a convenient way to write the action in terms of integrating the symplectic form over the disk rather than the connection over the boundary. But now, because the definition of the integration cycle depends on the disk has become real. And I meant to have here a picture where the disk was shaded to help you visualize that it was real. So I wrote I've shaded the disk because we're doing a path integral on the disk, not on the boundary. I've set h bar equals 1 in the final formulas, except I didn't do that. But I intended to set h bar equals 1 in the final formulas, because although deformation quantization is usually formulated over a formal power series ring, we're interested in a situation where it makes sense to take h bar to be a non-zero constant. But also, since I haven't told you how to normalize this symplectic form, we lose no generality by setting h bar to 1. But really I said h bar to 1 because we want deformation quantization of y to be exact, not just a formal procedure over a ring of formal power series. That's why I say that y should be nice. So how is this related to what I've been telling you? Well, you can show that the integration cycle that corresponds to the maps that extend over D is precisely what you get from the A model of Y if the brane on the boundary is this canonical Coisotropic brane, BCC. I'll get back to that in more detail in a moment. So a nice case where deformation quantization is exact is that Y equals T star W is a cotension bundle of some other complex manifold W with the standard complex symplectic structure. Then you can show that the deformation quantized ring curly A of holomorphic functions is a ring of holomorphic differential operators acting on the line bundle K to the 1/2 over W, where K is the canonical bundle of W. If you sheafify the situation by working locally on W, you get the sheaf of holomorphic differential operators in W acting on K to the 1/2. In the case of geometric Langlands, Y is the Higgs bundle moduli space. It's birational according to Hitchin to T star of M of G. So A, which is Hom of BCC to itself, when you sheafify it, is the sheaf of holomorphic differential operators on M of G. In the statement, I'm using the fact that the brane BCC leads to this construction with this particular integration cycle of maps that extend pseudo-holomorphically on the disk. Well, in this case, holomorphically, because K is integrable. So in other words, okay, so Hom from BCC to itself is the sheaf of holomorphic differential operators on the moduli space of bundles, as opposed to the Higgs bundle moduli space. So if B is any other brane, then Hom from B to BCC is going to be a module for the quantum deformed ring of holomorphic functions on Y, which is Hom from BCC to itself. So in other words, the category on the A model side of the geometric Langlands duality is the category of, roughly speaking, D modules on M of G. Mathematically, you really want D modules on the stack on G, not the finite dimensional moduli space. Physically, what that means is that it's important that a version of BCC can be defined directly in 4 dimensions, not only after reducing to 2 dimensions. Kapustin and I had a version of that, but Zagayotov and I improved it a few years later. The brane BCC descends from a deformed version of Neumann boundary conditions. Neumann for gauge fields, which say that the curvature with the contracted with the normal vector vanishes. By deformed Neumann, I just mean that that contraction can be expressed in terms of boundary fields without normal derivatives. So this deformed Neumann boundary condition can be realized in string theory by a D3 NS5 system with a Chan-Patan curvature on the NS5 brane. The reason that is important is that it tells us how to describe the dual, which will be important on Tuesday, I guess. So the dual is a similar D3, D5 system. Well, okay. So as I said, the description shows what is the dual. It comes from a D3, D5 system. And that made it possible to answer a question that earlier had been obscure from a physical point of view, though the answer was known mathematically through the work of Balanson and Drinfeld. What's the B model dual of BCC? So BCC is an A brane, so its dual will be a B brane. In other words, a coherent sheaf for a complex of coherent sheaves on the Higgs bundle moduli space. And the dual is a very special Lagrangian submanifold of the moduli space for the dual group. And well, we'll need some details about that dual on Tuesday. In summary, the main ideas in the correspondence between gauge theory and geometric Langlands are the following. One is electromagnetic duality of supersymmetric gauge theory in 4 dimensions. Then there's twisting to make a dual pair of topological field theories. compactification to 2 dimensions on a Riemann surface C. The dual theories have dual sets of line operators with the 't Hooft operators that correspond to geometric Hecke transformations and the more elementary dual Wilson operators. Then there's the distinguished brane BCC that establishes a map from A-branes to D modules. On the other side, there are B-branes on the Higgs bundle moduli space in the complex structure in which it parametrizes flat bundles with complex structure groups. Now, I'll stop for a moment for questions, and then we'll go into a slightly different topic for the rest.
Okay, we have a few questions in the chat. Maybe we can bring those up. So there was a question by Jacques Distler asking, what is the 4-dimensional interpretation of the Kapustin-Orlov coisotropic brane condition?
Well, Edward explained it many slides later than when I asked it.
I explained it in this context.
In this context, yeah. Maybe you want to say some more.
Well, I don't know a good example to explain it in other than this context. So I don't have much to add to what I said. Let me look at the questions in the chat to see if there's some I should answer.
Well, there is a question by Aswin, which is asking about abelian versus non-abelian, but I didn't understand the question, so maybe Aswin can ask it again.
He asked, what's the non-abelian Hecke modification? Well, 't Hooft operators correspond to Hecke modifications for whatever the gauge group is. So for the abelian gauge group, they're elementary. For the non-abelian gauge group, I described them, but they're a little bit less elementary. But regardless, 't Hooft operators correspond to Hecke operators. By the way, that's the part of the story that gave me the most trouble to understand. Since about
my question was slightly different, Edward.
Okay, go ahead.
So in the literature, I've seen 2 variants of the Hecke operators. Ones that sort of leave the Higgs field invariant. They are sometimes called abelianized Hecke operators. And the other ones that are sort of more general. There's no such condition on leaving the Higgs field invariant.
Oh, well, I described the Hecke transformations for bundles.
Yeah,
and there is a story for Hecke transformations for Higgs bundles, which we need. Well, I was going to skip explaining it, to be honest. You see, I reduced from 4-dimensional equations to 3-dimensional equations by taking things to be time independent, and also simplified by taking the Higgs field to be 0. I should have written some more general equations than the Bogomolny equations, and then I would have deduced what are Hecke transformations for Higgs bundles.
So, but the statement is that 2 operators.
Well, 't Hooft operators, we have to study 't Hooft operators here in the generality of Higgs bundles. And I've explained it in most detail, not in the original paper with Kapustin, but in a later paper. It was called More on Gauge Theory and Geometric Langlands. But you see, Hecke operators for Higgs bundles, roughly speaking, do nothing to the Higgs field. The only thing is that doing nothing to the Higgs field doesn't make sense for a generic Hecke transformation. If you make a generic Hecke transformation, you'll find that, think of the Higgs field the way Hitchin said, as a map from E to E tensor K, where E is a bundle. Then you try to replace E with E prime by a Hecke transformation. Then you'll find out that generically the Higgs field, first of all, you can interpret it, except possibly with poles, as a map from E prime to E prime tensor K. But as a map from E prime to E prime tensor K, it generically will have a pole. So when there is a Higgs field, generic Hecke transformations aren't allowed. So Hecke transformations do nothing to the Higgs field, but the Higgs field puts a constraint on the bundle. E has to be such that it makes sense to do nothing to the Higgs field. It's an important part of the story, which I actually wasn't planning to lecture about. And where I did try to explain it, well, it's very briefly stated in the paper I wrote with Gauger that just came out, which is on the subject of Tuesday's lecture. But where I explained it in more detail was in that paper, Gauge Theory and Geometric Langlands, more on Gauge Theory and Geometric Langlands. Maybe at the end, if you want more, we could discuss it in more detail. But there's only one sensible thing for Hecke transformations to mean on Higgs bundles, and that's what they mean. You modify the bundle by a Hecke transformation, and then you see whether that made any sense for the Higgs field. And if it doesn't, you go back to Go and only consider Hecke transformations that do make sense. That's the best short explanation I can give.
There are a
maybe-
couple of general questions. One is,
Let's only have questions on the lecture, during the lecture.
no, there are a couple of general questions about the lecture. So there is one about the Langlands duality on the group level, whether it's the Goddard-Olive-Newitz duality.
Yes, Langlands duality was discovered independently by Goddard, Newitz, and Olive. And I believe it was Atiyah who made the connection between the two. Certainly he's the one who told me about it.
And there was another question about the monopole discussion, if anything will happen if one has monopoles without singularities.
Well, we consider all solutions of the Bogomolny equations, which have prescribed singularities, and they have other boundary conditions that I didn't state in detail. So the boundary conditions might or might not allow you to have smooth monopoles as well as the singularities. If they do, then we have them. If not, not. In general, the A model localizes on some equations. Those equations have smooth monopoles as solutions. But the boundary conditions depends on the branes and exactly what we're doing. So there might be smooth monopoles in the discussion. I wasn't specific and detailed enough for your question to have a definite answer, but in general, all solutions of the Bogomolny equations are allowed, and even all solutions of more general equations that I didn't write. So we definitely might have smooth monopoles. Knowing about smooth monopoles is important, certainly. Is there another general
Okay,
question?
I think this is it, so we can just move on.
Now, my story so far involves deformation quantization, not quantization. And the difference is important. I have a slide to explain it, although in principle, if you all heard yesterday's lecture, it might be unnecessary. But because the point tends to cause confusion, I will anyway have a slide to explain the difference. I'll consider the concrete example of a two-sphere, viewed as a symplectic manifold with its usual rotation invariant symplectic form. In deformation quantization, we'd start with the commutative algebra functions of x, y, and z, maybe with real coefficients, maybe complex ones, and we want to deform it to a non-commutative algebra. In general, you say that the leading non-commutative deformation should agree with the Poisson bracket, and then you ask if there's a family of associative algebras, maybe over power series ring and H bar, maybe over formal power series with that property. And in this case, we could set H bar to a complex constant if we want to. In this case, we can't. In this particular case, we can just write down the answer, which is given by the S2 algebra. So the algebra generated by x, y, and z with these relations, along with this relation, or a quantum deformed version of this relation, where you add a constant, is the answer for deformation quantization of this problem. That makes sense for any value of j squared, and it's not quantization. Quantization means finding a Hilbert space H of the appropriate size for the algebra to act on. It doesn't exist for arbitrary j. To construct H, you have to quantize the parameter j, which means set it to preferred values, at which the Hilbert space exists. These special values correspond to the angular momentum in the real world of electrons, atoms, molecules, and so on. And it's because of the last step where the parameters are quantized that the subject is called quantization. So Gukov and I asked whether the A model in this general setup can describe quantization and not just deformation quantization. The answer is yes, under certain conditions. Recall that in general, we're discussing a complex symplectic manifold, where geometric Langlands Y is the moduli space of Higgs bundles, viewed as a real symplectic manifold with symplectic form M omega. So let's discuss Lagrangian A-branes, that is, brane supported on a submanifold L that's Lagrangian for M omega. In many of the examples that are important in geometric Langlands, L is actually a complex Lagrangian submanifold. That is, it's Lagrangian for omega, not just M omega. For instance, consider a skyscraper sheaf on the G-dual side, supported on a point in the dual moduli space. Well, its dual is a Lagrangian brane supported on a fiber of the Hitchin fibration for G. That's a complex Lagrangian submanifold. The reason this happened is that a point in the moduli space of the dual group is hyperholomorphic, meaning it's holomorphic for every complex structure. I'm just telling you that a point is a complex submanifold for every complex structure, and therefore, dually, its dual is going to have to be complex Lagrangian. And in general, if you take any hyperholomorphic sheaf for G dual, then its dual on the G side will have special properties. But a general L is not Lagrangian for omega, just as a coherent sheaf on the dual side need not be hyperholomorphic. So Gukov and I decided to consider the opposite case. We took an A-brane B whose support M is Lagrangian for M omega, as it must be by the definition of the A model, but is symplectic for real omega. So in doing this, we were stimulated by a number of prior contributions, of which the most direct was by Elliott and Zaslow, who had done illustrative computations in special cases. We argued that in this case, Hom from B to BCC is a quantization of M with symplectic structure real omega. So for example, if Y is an affine variety, the holomorphic functions on Y, which are deformation quantized to get the algebra of holomorphic functions, they can be regarded as analytic continuations of some real analytic functions on M. There are enough of them to be a reasonable quantum deformed algebra of observables. And then we showed that Hom from B to BCC is an A module, which has the appropriate properties to be a quantization of M. In fact, a formal argument reduces the description of the Hilbert space to quantizing M. So, well, I'll sort of say what the formal argument was. So B will be a rank 1 A-brane whose support M is Lagrangian for M omega and symplectic for real omega. So because it's Lagrangian for M omega, B is an A-brane. And because it's symplectic for real omega, we're going to get quantization. So the Chan-Paton bundle of B will be a unitary line bundle with curvature F. And we took the model to have a B field that I called B. I'll remind you in a moment what it was. So the Chan-Paton's bundle has to be such that F plus B is 0 on M. That's the A-brane condition in the presence of a B field. But we chose B equals omega J to get the situation that led to deformation quantization. So therefore, we need F equals minus omega J. Now, a pre-quantum line bundle in the sense of geometric quantization for quantization of M with symplectic structure omega J is supposed to be a unitary line bundle of curvature plus omega J. So we can take the Chan-Paton bundle of B to be L inverse, where L is a pre-quantum line bundle. Let me also write T for the unitary connection on L. So now Gukov and I considered the BCC-B strings. And we showed that at low energies, the effective action is just minus I times X star of T plus Q of something. So as I tried to explain yesterday, we can now sensibly define Hom from B to BCC to be a quantization of M with the pre-quantum line bundle L. In other words, we found a formal argument that shows that the supposedly well-defined problem of quantizing the BCC-B strings in the A model, which we believe is well-defined because Y had an ultraviolet had a complete hypercalorimetric and an ultraviolet complete sigma model. We have a formal reduction from a well-defined problem to this ill-defined problem plus massive degrees of freedom that are formally irrelevant. So in other words, the well-defined answer, the Hom in the A model, which came from the well-defined sigma model, we just defined to be a quantization of M with this pre-quantum line bundle L. So that's the sense in which we argued that the supposedly well-defined A model answers the problem of quantization of M with the symplectic structure real omega. And you can see that we really needed the sigma model to exist as an honest quantum field theory argument, since this was an argument that depended in a strong way on that quantum field theory really existing. It was not a formal construction. I actually have so far omitted a key point. What structure is needed for H, which is Hom from B to BCC, to be a Hilbert space, not just a vector space? First, there was a reason to describe the construction without this point yet, because in representation theory, it's often interesting to consider, in representation theory, for example, one considers representations of non-compact Lie groups that are considered interesting, admissible representations. They're actually not unitary, so one does not have a Hilbert space. So one has this, essentially the structures I've mentioned, but not the additional structure I'm about to mention that will give us a Hilbert space. But now I'm going to tell you what additional structure we need if we do want to get a unitary Hilbert space. And we definitely will want that for Tuesday. And we do want that if we want unitary representations of non-compact Lie groups, or compact ones for that matter. So if B1 and B2 are any two branes, the A model in general gives us a non-degenerate bilinear, not Hermitian pairing between the two Helm spaces in opposite orders. So to get a Hermitian inner product in one of them is the same as finding an antilinear map from one to the other. Gurkov and I showed that there is such an antilinear map, which I'll call theta tau, if there's an antiholomorphic map tau from Y to Y, with M as a component of its fixed point set. So theta tau is basically the product of CPT, which I'll call theta, times this operation tau. I won't discuss its definition and properties in detail, but I'll explain why you might intuitively expect that tau is what you would need. Suppose that holomorphic functions on Y act on H, and that H is a Hilbert space. Then you will have a notion of which holomorphic functions on Y are Hermitian. Well, existence of tau gives a natural notion. A holomorphic function on Y we consider real if it's real when restricted to M. If M is just a real submanifold of Y, but not the fixed point set of an anti-holomorphic map, then in general, we would not have any idea what holomorphic functions on Y should be considered real. So existence on Y is the structure that lets us guess what functions should be interpreted as Hermitian operators. And Gurkov and I argued that if you take theta tau, which is the product of tau and CPT, and use it to map from one to the other, then you do indeed get a Hermitian structure where the functions that are real on M become Hermitian operators. So that's what I've, okay, well, given tau, the Hermitian product on Ham B1, B2 for any pair of tau invariant branes is defined this way. It's always non-degenerate, but in this generality, it's not always positive definite. But in the case relevant to quantization, the pairing is positive definite if you're sufficiently close to a classical limit. And that's the situation we'll be in on Tuesday. Now to summarize a little bit, in this approach to quantization, if you have a real symplectic manifold M and you want to quantize it, you have to pick a complexification of M to a complex symplectic manifold Y with some appropriate properties. So one property is that the real part of its symplectic form should be the symplectic form you want to quantize. Another property is that the A model of Y should exist, well, the quantum sigma model of Y should exist as an ultraviolet complete theory. And Y should have this anti-holomorphic symmetry with M as a component of the fixed point set. So really we need Y to have a well-defined A model, including these coisotropic branes, not just in the sense of formal power series. But the only criterion we know for that is that Y should have a complete hyperkähler metric. So quantization by branes could be compared loosely to geometric quantization, which has been the closest to a systematic approach to quantization. In one case, to quantize M, you pick a polarization of M, and then you get a recipe for quantization. In the other case, you pick a complexification. Geometric quantization or quantization by branes can give good results if there's a natural polarization or natural complexification for the problem at hand. Gurkov and I didn't understand much about the relation between the two approaches, but motivated by an application, Gaiotto and I found a criterion in which the two agree. The basic idea is that they agree if the polarization used in geometric quantization can be analytically continued to a homomorphic polarization of the complexification used in brane quantization. That paper, unfortunately, isn't quite on the archive yet, but will be in a few days. So what we've said will hopefully serve as useful background on Tuesday for the work of Edinger, Frankel, and Kazdan. And as I've said, you might also be hearing more about that general subject from Teschner. Thank you.
Thank you very much. Let's thank Edward. We have a few questions in the chat, and maybe I can open the floor to questions if people want to ask something on the lecture or on the last part of the lecture that we've just heard. So there is actually a question in the chat that's more related to the yesterday's lecture, but maybe we can circle back to that at the end if we have enough time. I had a quick question about your UV completeness picture.
Yeah.
So that issue with the completeness of the hypercalorimetric is automatically solved in the Hitchin or flat connections moduli space. But if you want to do this formalism in general, say on cotangent bundles, then we don't have completeness.
That's correct.
And there is this fixing of that Hitchin came up with folding of the hypercalorimetric, introducing a singularity at the boundary of a disk bundle in the cotangent bundle and gluing another disk bundle so that we get a global complete hypercalorimetric, but with the singularity on the real submanifold. Will that somehow come into your picture and help with the quantization?
I'm not familiar with it, but it could, it might. You're correct to point out. Okay, pragmatically, the A model of a cotangent bundle has the needed properties, even though the logic with the complete hypercalorimetric doesn't apply. I would have a problem using that for the Higgs bundle moduli space, even though it's birational to a cotangent bundle, because I need to make duality statements, whereas a physicist, I would really want to rely upon the physics. But you're correct that there are facts which are true for the cotangent bundle, which aren't explained by anything I've said. And I'm not familiar with this history of Hitchens you mentioned, and maybe it is a good approach. I think that would be extremely interesting to look at that as a physicist and see what conclusions one would draw. I'd like to also say that we don't really need it that much for geometric Langlands, but to make contact with what mathematicians say about cotangent bundles, we really want to sheafify along the base. And although that operation makes sense for everything I've said about it, physically it's a little unnatural. And so I'm not very satisfied. Okay, at points in some of my papers, when I've used that step, I've always been dissatisfied. And I'd like a better explanation. Either way to avoid that step or a way to make it look more natural physically, which I don't know. So I don't think it really bothers us for Tuesday's lecture when we say more about geometric Langlands, but it bothers me for other potential applications. It wouldn't bother a mathematician, I don't believe, because sheafification mathematically sounds way more natural than talking about ultraviolet complete sigma models. But as a physicist, it bothers me. I see a very long question in the chat.
Yeah, that's a question on yesterday's discussion, but I don't know if people have actually questions on today's lecture that they want to voice.
Well, the question, let me paraphrase the question, the long question in the chat. See, the question is written in the chat as if we start with y and we want to find m. But the usual problem of quantization, you start with m, a real symplectic manifold you want to quantize, and then you have to pick either a polarization or a y. And quantization by either approach won't be useful unless there's either a natural polarization or a natural complexification. And when there are natural complexifications, they're pretty scarce. But there might be a unique one, but if there's a family of them, then you have to worry about that. A famous case where there is a family is actually the moduli space of flat connections on a surface. Where the Narasimhan-Seshadri theorem gives a family of complex structures, each of which leads by Hitchen's theorem to a complete hypercalorimetric. But usually when a generic M won't have a good complexification. If there is a good complexification, it's going to be pretty rare. So that's at least a partial answer to the long question in the chat. I see two people with hands raised though. One is Aswin and one is P. I'm not sure who P is.
Hi, Edward. So my question is short. So I was curious if there is also a mirror version of the A model quantization picture. Like, is there like a B model approach to quantization as well?
Well, that's basically what we'll be doing Tuesday. Actually, but Sergei Gukhov, after our paper on branes and quantization, back in 2009 or so, Sergei wrote a paper on that. I think even this title of this conference or something. Okay. I saw something by Gukhov that suggested he's going in that direction again. But my view is that generically it's not that useful, because if you try to apply mirror symmetry to quantization, the results tend to be untransparent. But Tuesday's story is actually a case where it does give rather transparent results. So, I mean, we'll actually be applying mirror symmetry or S duality, electric magnetic duality, to quantization by branes on Tuesday. Pranav has a question.
Yeah, so I wanted to ask about this quantization construction. So the end result of the quantization depends only on the category of A-branes on this complexified space, right? The Fukaya category. It's all expressed in terms of endomorphisms of objects and HOMs.
It's the physicist version of the Fukaya category, which includes this coisotropic brane.
Right.
All right.
But that only depends on the underlying real symplectic structure of Y itself, right? And not on its complex structures and holomorphic, and its hypercalorimetric.
Well,
So
except it depended on the choice of the brane BCC. So in the A model, we picked this particular brane,
right.
and there were more structure enters. So that's where
I
the
see.
choice of complexification enters. So it could happen that there are different choices we could have made for Y. And then we would get different potential answers. And we might not know how to prove that they're all the same.
I see. So the
But
choice
anyway,
of the
more structure did enter because we worked in the A model, which only depends on the structure you said. But then we picked a particular brane, BCC, in the A model. And that definitely involved more structure.
Right. So, but also the choice of a brane in the A model, even the Lagrangian brane that you use, B itself.
Yes.
So a brane is more data than just a submanifold, right? So where
We
is
picked
that?
the pre-quantum line bundle.
Right.
To find the brane, the way I said it was we had to pick what physicists call the Chan-Patan bundle. But in this case, the Chan-Patan bundle was the inverse of what would be called a pre-quantum line bundle in geometric Langlands. In geometric quantization. In geometric quantization, the first step is to pick a line bundle with curvature omega j. It's called a pre-quantum line bundle. And then with the help of the polarization, you pick a good class of sections of it, which is called the quantum Hilbert space. I didn't explain that yesterday because there was too much to explain. But the first step in geometric quantization is to pick such an L. And we used L inverse. So effectively, we used the same data you would use in geometric quantization, a choice of L. But geometric quantization with the choice of L only wouldn't tell us how to construct a Hilbert space. And without more structure, you can't. The more structure we used was the complexification and the choice of this brane BCC. So we started with the pre-quantum line bundle, but then we didn't continue with the polarization. We continued with this complexification and arrived at a Hilbert space.
Thanks.
I had a slightly related question actually here about the positivity issue. You said that you can actually argue that positivity holds for the pairing with the corresponding real structure if you're close to a classical limit.
Yes.
Where is that coming from?
Well,
I mean, what forces the positivity? Because like in other situations of geometric quantization, we have natural pairings that are not positive.
well, The one I know is if you have an indefinite complex polarization, the pairing isn't going to be obviously positive. Is that what you have in mind, or do you have a different?
Well, yeah, no, I was thinking more concretely, like for the conformal blocks, for example, there is this unitarity problem for your connection, right?
Yes.
And there is always an indefinite Hermitian pairing there that's coming from Koch theory. That's definitely flat for the connection, but that's not the one that people want, right? So we're looking for a different pairing.
That one does not come naturally from geometric quantization. To me, where geometric quantization does not naturally lead to positivity is when the case I know in real life, where the answer suggested by geometric quantization might lack positivity, is when you quantize with a complex polarization that's not scalar.
Mm-hmm.
The line bundle could have cohomology in different degrees, and there's no natural positivity. So I don't like your example, honestly, because I think you're telling a mathematical structure that is present here, but it's not natural in geometric quantization. So,
but so in your setting, what forces the positivity? What's the reason for it to happen?
pragmatic is that we just are quantizing a cotangent bundle. So we just have an L2 space of.
I see.
But if we instead had it, that will be the case Tuesday. But if instead we had see, when does geometric quantization give a geometric quantization with an indefinite scalar polarization, or not sufficiently ample line bundle, I should have also said. Even if you have a scalar polarization, if the pre-quantum line bundle is not sufficiently ample.
It's not positive, yeah.
Well, even if it's positive, even if it's ample, if it's not sufficiently ample, geometric quantization doesn't necessarily lead to positivity. So when I said sufficiently close to a classical limit, for geometric quantization, that would mean that the complex polarization is scalar and the line bundle is sufficiently ample. So I'm not claiming more than the fact that we would get positivity in a case where positivity would be clear in geometric quantization, which means either a cotangent bundle or else a sufficiently ample situation for a scalar polarization. Actually, if L is sufficiently ample, I imagine you can get away with even an indefinite complex polarization. Well, okay, I'm going out on a limb. I haven't thought about that properly.
Thanks.
There are real life examples of this that I'm extremely interested in, which I mentioned yesterday and which also I'll mention again Monday. That's Chern-Simon's theory with a non-compact real form. So there's no polarization of the space of gauge fields that has all the properties you'd want. You can have your choice of a scalar polarization that's not gauge invariant or a gauge invariant polarization that's not scalar. And either way, I don't personally know what to do. I see Ali has a question.
Yeah, Ali, go ahead.
Yes. Hi. So I'm sorry if you already said this, but my question was that once you pick a complexification, why is the choice of canonical isotropic brane unique? Or can you have more than one choices?
Well, we picked a complexification, and it was required to have the property that omega, the real symplectic form, analytically continued to a holomorphic symplectic form on the complexification.
Okay.
Then we take the A model symplectic form to be the imaginary part of that holomorphic symplectic form. So that's unique. And then when we construct what I call BCC, I use only the real and imaginary parts of the holomorphic 2 form in constructing them. So all that is unique because by definition, they were an analytic continuation of the real symplectic form we started with.
Okay.
We had a real situation we want to quantize. We analytically continued it. And the data we used was only the data that we got automatically from that analytic continuation.
Thank you.
Sure.
Any more questions?
I see Ahsan has a question.
Hi. So my question is slightly related to Aswin's question. So if I think about this, the steps that you apply to, so you didn't directly mention this in the lecture, so maybe it's not too relevant. But if you think about the steps you apply to derive, let's say, Kobanov homology, you're starting with Chern-Simons theory, analytically continuing, and then applying S-duality, and then lifting to 5 dimensions.
Yes.
So I'm wondering if there's some analog of this that you can apply to brane quantization, where you're analytically continuing this action to 2 dimensions. Whether you can apply mirror symmetry and somehow lift to 3 dimensions to get something interesting.
Well, there are several potential questions in what you're saying.
Mhm.
So,
Basically, it's vaguely, I'm just asking about whether there's some natural 3-dimensional lift of brane quantization.
maybe I'd recommend to think about it.
Mhm.
I think maybe I should only say that. I explained a kind of analytically continued version of deformation quantization where you use a different integration cycle.
Mhm.
Now, a question you could ask, I've never gotten anywhere with this question, but the question you could ask is there, in some sense, an analytically continued version of quantization rather than deformation quantization, where you use not a different integration cycle, but a different something suggested by the same picture? That's one question which you might ask.
Mhm.
I never got anywhere by asking it, but it's a question.
All right, thanks.
Okay, maybe it's a good point to stop, and people can ask questions in the Slack forum.